Hello and welcome. This is Joseph Kennelly. I am one of the students in your class, and this is my final project, all set up and ready to go. I will take you through it as we go. What I decided to research for this class was utilizing context-rich problems to advance the problem-solving skills of my students. That was my main focus that I wanted to get through, and this is my journey as I went through and discovered a few more things other than just about problem solving. So, first and foremost, why did I want to do this? So one of the things that I've been seeing in my students is that many of them have this equation-seeking behavior where they go through, they look at a problem, and immediately they're looking for an equation, or they're looking for what's the missing, and that's just not really a great way of solving problems, especially if they're going to advance into any kind of upper-level problem solving as they get older. Secondly is having students work in groups. I want to have my classroom be more student and group centered because what I've been finding is that a lot of the students don't know how to work effectively in a group, or when they do work in a group, they don't use each other's minds. They just kind of argue, or one kid takes responsibility and everyone else just kind of copies the work. Another thing that I really wanted to look at was, how do we help students make effective decisions? Now, making a decision is easy. Making an effective decision is what a lot of our students struggle with. An effective decision meaning that a decision that they make that actually helps promote or moves them further in the problem-solving process. So being able to say, this is important, this is not important. What else I wanted to look at was how can I scaffold these groups and this work for students to make it the most effective for them, as well as how much and how often do I need to continue these practices in order to make them effective for my students. Now, as I did this, I looked at 4 main pieces of information, although I did gather a few other small random bits, but for the most part, these are the 4 things that I looked at. The first was Randall Knight's 5 Lessons on Physics. This was my real jumping off point. I downloaded or bought his book off Amazon right before I actually started the class, and as I was reading it, I realized this is exactly one of the jumping off points I needed for this class and this project. And what he really focuses on is teaching active physics, meaning keeping your students engaged and active and moving around and engaging in physics hands-on every single day in class, either with problem solving or with labs or with some experiment that can really get them fired up. With that, he explains that students need to be constantly working with their peers, because that peer-to-peer interaction is what builds better understanding and deeper understanding within our students, as well as finally confront preconceptions and disprove them. A lot of times we talk about this in science as misconceptions. These misconceptions, which I actually like preconceptions better, it sounds better, but they're things that students misunderstand, and they think one way when a lot of times it's counterintuitive, and you have to recorrect their knowledge. Next, we have the Cooperative Problem Solving in Physics Users Manual by Kenneth and Patricia Heller. The Hellers really map out this wonderful program. It's utilizing this whole master framework about problem solving and how to organize a problem and how to organize your thinking and work like an expert problem solver and those expert physicists that we aspire to be. With that, the problems that students solve can't just be simple, very obvious problems that a lot of times you see in a textbook. You have to make what's called a context-rich problem, which we'll review over in a little bit of what those look like, and I'll read an example for you later. But these are examples that are not necessarily textbook problems, but are problems that have a lot more detail to them, a lot more information, and makes the students really engage with the problem itself. Now, with that, they suggest building it up over the course of an entire semester, so not just at one time. They suggest building it up over the semester, not making it all one big shot. Sadly, I had to do because it was the end of the semester, but again, I will still respond with some of the takeaways that I had from that experience and what I still learned from it. Now, with that, they have this huge framework. It's a whole double-sided page worth of framework for them to solve these problems with, but utilizing that framework really helps students to expand their knowledge and really dive deeper into the physics and the actual problem itself to really get a good understanding of it, which that framework includes focusing the problem, describing the physics, planning the solution, choosing the plan, and evaluating the solution. Now, I did use 2 other sources. These were just minor sources, but still very useful. One was Teaching Problem Solving Through Cooperative Grouping, which again is by Patricia Heller, but a little bit further back in 1991, where she was first starting out her research for that problem solving manual. But some key takeaways from that text were the grouping sizes, so ideally sizes of 3, heterogeneous groups with at least 3 roles within that group, which including manager, skeptic, and checker recorder. Now, the whole idea behind this is that students don't just solve the problem, but then they also present the problem, and your students who aren't writing are the ones presenting, so that way they make sure that they understood all pieces of information. And then when all students have presented their ideas and their final answers, you discuss it with all the students, correct their mistakes, discuss with them what pitfalls and wrong turns they may have made. Lastly, we had the Physics, a Contemporary Model, Volume 1 and 2 by Randall Knight, put forth in 1997. Again, this is much more of a resource. It's actually a textbook, which I did not realize when I first ordered them. But they are both textbooks, but they are full of these real-world physics context problems and those context-rich problems. For more of a college level, but those helped me to design high school version levels of these problems. Yeah, cool, that's still going. So, putting problem solving into action. Now, this was kind of my main focal point of what I was trying to do and what I did do as the course went on and as my project went on. The first thing I wanted to do was create a lesson to introduce the entire topic of these group problem solving experiences. Many of my students have done nothing but problem solving by themselves, and they've never really had that experience or opportunity to work with their peers on a big meaty problem like the ones that we are going to give and get into in our context-rich problems. Now, what we had to do with this was we had to essentially create an entire presentation about what is problem solving and how do we become better at it. Many of my students had never read anything about it, had never had any experience dealing with this kind of high-level problem solving. The only thing they'd ever had to do was just find a few answers, and what I wanted to do was make sure that they were comfortable with that. Now, with that presentation, I also introduced the roles and the framework within that. It was a very heavy conversation, but the way we started out was we started off with this conversation about what do expert problem solvers do, giving them an example of one of these context-rich problems, then not asking them to solve it, but just saying, hey, how would you go about your ideas and organize your thoughts in order to solve this problem, which after going through their ideas and then showing them how I would have gone through it, they could see the differences visually because we web mapped it out, and they were actually able to say, yeah, no, I want to be able to think like that. That makes way more sense, which was really great for me because it meant that all my time and effort going into this research was really going to pay off. Now, with that, I also had to create a list of group roles determined from that research, as you saw, from the Hellers. Those group roles were pretty solid, but I need to add a fourth because I have groups of 4 in my class, and because I can't really jump down to groups of 3, just due to material sizes and amount of space in my room. Next, my goal was to, and this is kind of an ongoing goal still, which is to create a list of 4 to 5 context-rich problems for each unit that I was able to teach. Now, unluckily, due to the lateness of my implementation of this, I only had about 2 weeks to really get it into my class and use it in my class. So I got about 3 problems for this unit, which is waves. But again, this will be an ongoing process, not something that's just going to end after this project. And I plan to have at least 4 or 5 problems like this per unit. So essentially, throughout the course of the year, 7 units plus 4 or 5 problems, in total around 28 to 35 problems total for students to interact with and challenge themselves with throughout the year. So I taught the framework, I modeled it for my students, and then my only major thing to change would be to start this at the beginning of the school year instead of right at the end in those last 3 weeks of school, right before finals. So that first lesson, as I said, I presented them the framework. I discussed with them how to go through this process and how to organize their thinking. And so what we did was we just wanted in this first lesson to get them familiar with the framework, as well as get them to attempt a problem, see if they can start to organize their thinking a little bit after one exemplar demonstration. So it was split up into 2 class periods. The first class period was just introduction to problem solving and how that is going to go, and how to use this framework and what this framework is, and why we want to go through these different steps, right? Why do we want to organize our thinking in this way, and why does it make the most sense? So what we did is we, after going through those different aspects, as well as going through the group roles with students, I went through and I modeled what this looked like. I wish I had a video to show you, but it was a model of exactly what I would go through as I read through the problem. So here's an example of the exemplar that I did with my students. This is exactly what I did in front of them, word for word, on a document camera, working through the problem as I would, talking it through with the students, and discussing my own thinking as I went through. And I'm going to read the problem just so you can kind of get an idea of what a context-rich problem would sound like. So something on the order of, over the summer, you are hired to work for a zoological society that are studying brown bats and their diet. They know that bats can eat insects as large as 2 centimeters, but have yet to determine the smallest insects they can find using echolocation. Remember from your physics class, and the speed of sound in air is 340 meters per second. They have told you that a bat's vocal cords vibrate with a period of 1.6 times 10 to the negative 5th seconds, and that their ears can detect and reflect the reflected waves at the same wavelength and frequency as they produce. So, as you can see, it's not a very straightforward problem. There's a lot of things students have to kind of work out for their own. So kind of to explain a little bit more of the process, the first part of this problem solving process is to focus your problem. So get a picture going, see what you can think of. After that, you want to go through and just figure out, what's the question actually asking me to solve? What do I need to find in this problem? And so that was our next piece. And the last piece is the approach. Well, what do you think you're going to have to do in order to solve this problem? What different steps and occurrences might you need to find? What different information might you need to find in order to get to that final problem? So that's the focusing of your problem. Next is on to describing our physics. Describing the physics, we need to draw a physics diagram. So this could mean a motion diagram. This could mean a force diagram. It could mean whatever is really necessary. So for this case, we drew a wave diagram of a sound wavefront. With all of our variables defined, because we want to make sure everything that we know is on that diagram, and we have it defined with a variable so we know exactly what equations we might need to use. Next, we list our target variable. So what lines up with our target variable should line up with our main question of what those two things are asking. And lastly, the quantitative relationship, which is what equations are we going to need to use to potentially find this answer. So we go on to planning our solution, which you see on the right there, finding your frequency, finding your wavelength, then which is where we do all the algebraic solutioning for this problem. We don't actually put in any numbers until the very end. That way we keep all of our numbers safe, we don't mess up any calculation, and we also can then check our units, which is down here. In physics, this is a really key skill to be able to do. Many of our students never check units. It's something that I did actually a very poor job of teaching when I taught this as an exemplar and as the unit went on, because I was kind of in a rush. It's something that next year, in the beginning of the year, I look forward to changing a little bit. Next, we go on to executing our plan, which is where we plug in our numbers into our 2 equations and we get out with our answer. And lastly is evaluate the answer. And this is a step that many students always forget to check. They always forget to check their work and evaluate their answers. Does our answer make sense? Is it in the right units? Isn't a reasonable answer? If we're talking about a bug, if it's the size of an atom, does that really make sense? Things like that. So going through that, is it reasonable? Is it complete? Making sure all of our answers are in a complete sentence that actually answers the question, right? So that's our exemplar. So now we move on to student work. These students, this was their first attempt at a problem like this from the day following, because we didn't have time in our first class. So students started on this the day following, and they had an opportunity to work for 45 minutes on this problem. These 2 students, Damari and Taeyeon, began working. In general, these 2 students are very apprehensive about doing work. They do not like to do work. They do not like to engage with other people. But the 2 of them found success in this. The 2 of them were able to discuss with each other and talk with each other as the problem went on. They did kind of change roles and trade roles every once in a while, because one of them wanted to write on the whiteboard, one of them did not. And so they traded roles when necessary. But as you can see, they were able to draw a picture. Maybe that initial picture wasn't great, but again, for a starting off point, it's not too bad. As you can see, they were able to define what the question was, what are they looking for, what things they might need to find, and then work their way through the problem itself. On the right, you see where the blue writing ends. They kind of stopped there because that's as far as they got. The black that you see on the right is from what they gathered from their peers as the rest of the problem continued, and as we reviewed it as a class. Group 1, as you can see, a little bit more cleaned up, a little bit more information, a little more process of showing their work. I do not remember the name of these students off the top of my head, but as you can see, they went through and they really were able to clean up their information and really figure some things out. A few things, they made some minor mistakes here and there, trying to determine what they were really looking for, and they're describing the physics and they forgot to define a few variables. But again, this was their first attempt at something like this, so moving through the problem, you can see that they were mildly successful. And very similarly with group 3, very similar to group 2, the first group, Damari and Tayan, Kaylee, Melissa, and Cameron, as you can see, very similarly, were not able to get through the entire problem, but they were able to get up to that point, which they could discuss exactly what the process that they needed to go through, but were not able to have enough time to finish and execute their plan and evaluate their answers. So, moving on to day 2. Excuse me, I'm just need to check, make sure we're still recording, which we are. Wonderful. Solving context-rich problems, dealing with a Doppler effect. So their second experience with this, after we did our wave problem, like we did, we reviewed that with the class, and we discussed some of the major issues or pitfalls that they may have gone through. Now, what we did next was we introduced a much more complicated problem, something that really, really needed this framework, which had to do with echolocation. So this time, our goal was to not necessarily focus on the math, but was to make sure students feel comfortable with the framework and feel comfortable using that framework and actually going through and answering those questions and feeling free to make mistakes, because this is kind of what taking and doing physics is about. It's being able to make mistakes, backtrack, and move forward. We also wanted to see how well they would be able to utilize this framework with a little bit less help from me. So again, I introduced that new topic, we discussed the topic, and to give students a little bit of context, which was the Doppler effect, which is a really cool effect. If you have time, go and research it, but pretty much, essentially, it's a change in frequency depending on how an object moves. Now, what I did is I modeled for my students exactly what I wanted them to do and how to use the framework in a very similar problem, but not the same problem. And that's kind of the key. Is okay, let me show you something that's going to, one, use this equation, but use it in a different way than I want you to use it. So, modeled that for my students, had them ask any questions, worked with them through that problem, and then said, okay, now it's your turn. Again, giving students the opportunity to attempt the problem for 30 minutes, and then we reviewed the problem. So, as you can see, much more work on it, much more involved. Our diagrams might not be as good, but you can see they're thinking all the same as they go through, which is really wonderful. Students like Melissa have had a really hard time all throughout this school year with displaying her work and trying problems. Melissa is a student who if you looked at some of her previous work, you would see like maybe a sentence or two or maybe a little bit of a starting of a problem, but never a complete problem. This is her going completely through the problem, being able to find success in that by following our framework here. And granted, this is a girl who, when you gave her a simple problem out of the textbook, was not able to do it, yet here on a complex problem, she was finding much more success. Similarly here, Jose is also a very good student, but sorry if it's a little hard to read. He wrote with 2 markers on either side. But as you can see, he's a much more detail-oriented student when it comes to drawing. His drawings are very, very specific at exactly what he knew was happening, and he was able to show a little bit more detail in his drawings, which then allowed him to find more success in his planning of his solution and executing that plan. And then lastly, we have Ernesto, who is an A student if it weren't for his attendance, but as you can see, again, very detail oriented, has his diagram really done out well, has everything written down, and going through that process very well. Again, these are recorders for different groups, so these are not students who did this on their own. They recorded this from their group's knowledge, and so working with their peers was able to pull this information and work themselves all the way through it. They may have had about 45 minutes to an hour on this problem. I think I gave them a little bit more time just because it was such a meaty problem and it was still a very new idea. This was about 2 to 3 days after that initial problem that you saw, where the students were very all over the place. Now, one of the things that discussing with the readings was that students need to be able to actually find value in why they need to be able to do this. And so part of that is actually putting a problem like this on their exams and having them have an experience with their peers where they get to use their peers as well as themselves to solve these high-level problems. So what I did was I included one question for all of them to do as a group, as well as one question for all of them to do on the final exam itself. So this problem was the last one I did for them as a group before they took their final. It happened about 2 days before their final, and I was not actually checking to see if they could do the whole problem. In this, I was more looking to see if they could set up the problem right and really focus the problem in those first 2 parts of our framework, which going into next year is the first thing I'm going to focus on with my students, because the second part becomes almost trivial if you can get the first setup part right initially. So I want to really look and see if they could get this real setup done well for the beginning of each problem. So I only graded them on those 2 parts for this part of their exam. So again, we're looking for attempts, no blank pages. Even if it's incorrect, our focus was grading the correct setup of the problem. Now, what we did is we gave students the opportunity to work with their students in a different new context-rich problem, potentially had something from everything that we've talked about in the unit. So this was waves, light, sound, Doppler effect, all those wonderful things get thrown in the mix. And then students received minimal help from me as they had about 30 minutes to work on this problem. This one, they had a hard 30 minutes to work on the problem and get as far as they could. And as you can see, in groups 1 and 2, both of these are 2 different periods, but as you can see, as they went through, they were able to begin to diagram, especially group 1 on the left, which is a higher level group. Students were able to diagram, really write out their information and figure out what they were doing. When they got to describing the physics, their diagram is extremely detailed, although they did have a little issue once they started to move towards the back and quantitizing the relationships. Whereas group 2, which was my third period, Kiel and Carlos were able to go through the whole process and really dive deep into what they were looking for. Then we have group 3 and group 4. Again, both groups were able to show their work, really give some detailed drawings and some detailed examples, really be able to verify everything that they were looking for right before they started to go into it. I believe group 4 actually got all the way through the problem, whereas the rest of the groups did not have the time. Again, that comes with more practice and just the students you have in your group. What we have here is the actual rubric that they were graded on. So some students got a full, this was for one of the previous problems, but this is the rubric. Again, it's a 5-point scale determining like how well students were able to do. Sorry, that's not as clear as it should be. I'll see if I can attach that when I attach this presentation and a few other things to that final project. But they were allowed to be graded on each aspect, not necessarily the whole problem, but different aspects of the problem and how well are they doing that aspect as a group, which sadly I did not get an opportunity to share with them. In the future, that is something that I will do. So what am I taking away from this? What were some of the good things, some of the bad things of this process, and how things are going? Sorry, just double checking again. So on the plus side, high student engagement, and I mean high. Every single student's head was thinking, every student was asking questions, everyone knew what they were responsible for doing, and everyone was going through that process who was engaged in it. All students were also involved in the diagrams, actually being able to look at a picture and tell me what it meant. They could describe what was going on in the problem itself. And they could all describe the goal, what they were actually trying to figure out in the problem. Yeah, some of them it took a little bit of prodding, but I'd much rather have a little bit of prodding and have every student be able to tell me what the goal of a problem is than every student look at me like I have 9 heads and say, Mister, we have no idea. And they understood the purpose of the parts. All the different parts of the framework made sense to them. It actually helped them to organize their thinking, which a lot of them are very scatterbrained and go all over the place when they think about a problem. On the negative side, these are some things that I realized, not necessarily just about the process itself, but also just about the general time constraints and when I decided to do this. So one, I began this way too late in the year. I wish I had started it so much earlier, but again, you live and you learn, and it's something I will definitely take in with me into the beginning of next year. The other thing I'd like to do is tighten up each student's responsibilities. So what do they really need to do? So yeah, those 3 were good, and I added a 4th one. Oops. We're still okay. Sorry about that. Knocked my placeholder for that for my camera out. Oop. It'd help if the right side was out. My apologies. So, that rubric needs to be tightened up for students of what they're responsible for, as well as what they are in charge of for their reflection. Now, I should also do a little bit better job of demoing each person's responsibilities and how they can be an active member of that group. Lastly, we have a few last things. Again, students had trouble connecting past and current knowledge. Again, I think this and those next few points will really grow with when students come in doing this more often in the classroom. So it's not like a last 2 weeks of school thing where a lot of students are already apathetic, but it's from the very beginning, from the get-go, students are involved, problem solving, doing these things over and over and over again to really become comfortable with them. My last major takeaway actually is that I need to change how long a time I devote to each of these problems. It needs to be a full class period. For us, a class period is 1 hour and 45 minutes. But this gives the opportunity to maybe introduce a new topic, introduce a problem-solving example, or a problem-solving problem, give students a full half an hour to 45 minutes to work on it, have each student present, then give students to then correct a whole class-wise, and then have students go back and make their adjustments to their own problem, and then finally take a 10 to 15 minute reflection on the actual problem-solving process that they underwent. And I think that would be the most effective for my students. So, from all of this, I have 3 major takeaways to continue on in my classroom and to build myself as a teacher. First and foremost is students were able to learn how to problem solve best in groups, and very similar to my hypothesis and what I believed was that these students would work better and be able to achieve more in groups. And that was shown by the way that students were able to present, even though they were not the ones necessarily writing the problem itself, what the answer should be. They could talk about it. Students who had never really been active during our problem-solving sessions individually were active in discussing and talking and able to really understand what was going on. As a teacher, I must invest more time in discussing concepts with my students. I think too often I blow by them a little bit too fast to get to the problem solving because that's my focus a lot of times. But I think by devoting full-on periods to a problem solving issue or an attempt to problem solve, I believe that I can kind of really get deeper into those conceptual tasks and those conceptual discussions with students during those periods that are not problem solving. So maybe 1 problem solving day a week, 1 conceptual day a week. That includes a lab or some hands-on activity that students can really get a hold of. And lastly, student learning physics needs to be student-centered. I know this isn't really some of the things that I focused on, but these are some of my major things that I learned. And oh my God, the students need to be the center of learning physics. They need to be engaged and active during that process. Very similar to as Mr. Knight proposed, students work best and they learn best when they have hands-on physics. And this is something that I truly believe in my core. And that this process is only re-emphasized, and it has re-spurned me to want to go back to a way that I used to teach when I first started teaching during my student teaching back in Massachusetts, is that students need to be doing hands-on physics 100% of the time, and get away from focusing on the problem-solving aspect of it all the time that I have become obsessed with since I moved to Green Dot. Students can do physics, it just has to be with them rather than showing them physics. And so with that, that is the end of my reflections. again, these are the references for those books that I was discussing earlier, and thank you very much for your time. I appreciate your listening and your focus, and have a wonderful evening. Thank you. Good day.